All right, here we go with our topic 3.15 notes. This is the last topic in polars, and actually it's the last topic that will be on the AP exam, which is exciting. So the interesting concept involving polars is that basically if the graph is moving toward or away from the origin or pole at a given coordinate pair or on an interval, we can figure that out based on the sign of r and the rate of change of r. So in the last set of notes, we were talking about taking a polar graph and mapping it on the rectangular plane, because when the graph on the polar grid is moving toward the pole, that means the rectangular graph is moving toward the x-axis. Away from the pole meant away from the x-axis. Well, if we're looking just in polars, what we're going to see is that basically if r, the directed distance from the origin, and its rate of change are the same sign, the polar graph is moving away from the pole. And if r and its rate of change are opposite signs, then the graph is moving toward the pole. So basically, if r is 0 and increasing, which means its rate of change is positive, then the distance between the function and the origin, the pole, is increasing because we are the same sign. If r is positive, but its rate of change is negative, so opposite signs, we're going to find that the distance from the pole is decreasing. If r is negative, but increasing, so opposite signs, the distance from the pole is decreasing. And if r is negative and decreasing, the distance is going to be increasing. So the pattern that I've already said, if r is positive and increasing, so positive, increasing, negative, decreasing, then r is, the absolute value of r is increasing. That is, the distance from the pole is getting bigger. But if we have opposite signs, so positive, rate of change less than 0, or negative with the rate of change bigger than 0, then the distance from the pole is decreasing. So it's kind of hard to look at a polar graph and understand whether the graph is moving toward or away from the origin. So it's actually simpler to map it on a rectangular graph and determine if the graph is moving toward or away from the x-axis, just like we did in the 3.14 notes. So here we're going to work with the function f of theta equals 2 plus 2 cosine theta, and we have it graphed here. This is a cardioid. I mentioned that last lesson, but it effectively looks like a heart, so it's called a cardioid. If I look at this from a polar perspective, non-rectangular, and I want to know, is the graph moving toward or away from the origin on the interval from 0 to pi over 2? Well, let me just plot some points. If I input 0 into the function, I get out 4. That is going to be this point right here. If I input pi over 4, I get 2 plus rad 2. That's this point here. Actually, pi over 4 might be more right there. And then pi over 2, I get 2 out. So the question is, as we map on this interval, is the graph getting closer to or away from the pole? Well, here's what's happening. My r values, 4, 2 plus rad 2, and 2 are all positive. And because my r values are decreasing as my theta values are increasing, the rate of change of r is going to be negative. Again, that's because, for example, I'm going from 4 down to 2. I lost 2 as my theta values increased from 0 to pi over 2. That tells me that because the r values are decreasing while the theta values are increasing, that I've got a negative rate of change. Okay, the rectangular approach is actually a little bit simpler to do. What we're going to do is graph this function 2 plus 2 cosine x on the rectangular plane. So I first put in my midline at 2, and then I have an amplitude of 2. Amplitude of 2 gives me a maximum of 4, and the amplitude of 2 gives me a minimum of 0. And we have a period of 2 pi because our b value is 1, and of course cosine starts at the max, ends at the max. It's in the middle, halfway through, and then halfway between the min and the max, we cross the midline. And the question is, on the interval from 0 to 2 pi, 0 to pi over 2, are we moving toward the pole or away from the pole? Well, it's the same question as, are we moving toward the x-axis or away from the x-axis? And the answer is, we're moving toward the x-axis, which means the polar graph would be moving toward the pole, which is, by the way, the same conclusion up here. Because r was positive and a rate of change of r was negative, opposite signs, toward the pole. Same conclusion out of here. Toward the x-axis means toward the pole. So basically, in polar behavior, if the graph is moving toward the origin, that means the rectangular graph is moving toward the x-axis. If the graph in the polar grid is moving away from the origin, the graph in the rectangular grid is moving away from the x-axis. So let's look at a multiple choice problem to see how we can answer this. We have here the function r equals -1 plus sine theta, and they're asking us if on this interval what's happening, and it's really, you know, are we getting closer to the origin or not? Are we above the x-axis or not? So what we're going to do is plot this on the rectangular plane, first with a midline of -1. Since the amplitude here is 1, we've got a maximum here on the x-axis and a minimum at -2. There's no b value other than 1 in front of theta, so our period is 2 pi. With sine, we start at the midline, we head up, we go back to the midline, we head down, and we go back to the midline. So this is my sine graph, poorly drawn, but still there. And so the question is, on 0 to pi over 2, what is happening? Well, 0 to pi over 2 is this section right here. Notice that the graph is below the x-axis, but heading toward the x-axis. So we want below the x-axis, and we want getting closer to the origin, because that's the same thing as the rectangular graph getting closer to the x-axis. All right, the last concept, or maybe the second to last concept, is basically rates of change and extrema with polar graphs. So look at this polar rose that we looked at in 3.14, and if we just look at the first quadrant, we have this leaf of the polar rose. We think that there's a relative maximum right here. The maximum distance away from the origin looks like it's going to be at pi over 4. And it looks like, if we recall from last class, that's at 3 rad 3, which is at about 5.1. Okay, let's see if we can confirm that. Basically, if we take small intervals near pi over 4, and I filled this in for you because this is just some calculator work that it's not important to this lesson that you can calculate these rates of change. But basically, if the theta values go from 0.72 to 0.74, I can input those theta values into the function and do the average rate of change, and I'm going to get out these values. And what you're going to notice is that, by the way, pi over 4 is approximately 0.785. So right around between here and here is where I have my pi over 4 value, and notice my rates of change go from positive to negative. Well, that makes sense, because at a local maximum on a rectangular graph, the graph increases, then decreases, and we have a local max, because the slope of the graph goes from positive to negative. We can now hone in and really do this on some very small intervals of just 0.01 apart. Notice I have 0.785 as my breakpoint included, particularly because that's approximately pi over 4. Prior to pi over 4, my rates of change are positive. After pi over 4, my rates of change are negative. So just by a little bit of exploration and looking at average rates of change, I can confirm that in fact I have a relative maximum at pi over 4, because that is where the average rate of change of r with respect to theta changes from positive to negative. So this gives me my definition of a local max on a polar graph is when the average rate of change goes from positive to negative, and a local min would happen when the average rate of change goes from negative to positive. Okay, so we can use rates of change on polar graphs to approximate a value on a polar graph. Basically, this is a secant line equation. Here is my average rate of change of r with respect to theta. Here is my input value and my output value. So we know that the 0.6 pi over 4, and by the way, I'm so sorry that I just realized this, but I realized I gave you the wrong value here. and I'm correcting myself now. At pi over 4, my output value was 6. It was not a 3 rad 3. So that's my bad. I apologize for that. But does not change what I talked about. Okay, so we know that the point 6 pi over 4 is on the graph. What if we wanted to approximate theta at a nearby value? Well, what we can do is write a secant line equation using an input value, which is the angle, pi over 4, and an output value, which is the R value of 6. And then here we would input the average rate of change. And we're going to borrow that from a table we used up here. We could use either this guy or this guy because around pi over 4, I come in from the left or from the right. But now I'm realizing they're asking us specifically to approximate at 0.789. 0.789 sits on this interval. So we're going to use the average rate of change on that interval as the slope of this line, and that value is negative 0.11. And this is a secant line, and we can use the secant line to create what we call a secant line approximation. And I could, with my calculator, I could say negative 0.11. I could input 0.789 minus pi over 4 and add 6. And I'm going to do that on my calculator as we speak. Negative 0.11 times 0.789 minus pi divided by 4. Close parentheses, add 6, and I get an approximation. Oh my gosh, you guys. The approximation is 5.9996. So it's not very different than the actual output at pi over 4. But the point is that you can create a secant line and use the secant line to approximate another point on the curve. And then the last thing we're going to talk about here is that in a rectangular function, the average rate of change is the change in y based on the change in x. And the units are the change in units of y over the change in units of x. The average rate of change in a polar function is the rate at which the r value, or the distance from the origin, directed distance from the origin, changes based on changes in theta over a specific interval, and the average rate of change units are the units of r divided by the units of theta, which will always be in radians. And that does it for this lesson and for all of the content that will be covered for the AP exam.